We have an example problem here. A long, thin, straight wire with linear charge density, negative 45 nanocoulombs per meter, lies along the x-axis. Using Gauss's law, find the value of the electric field 10 centimeters radially out from the middle of the wire. Okay, so long, straight wire. They're telling us that we have a linear charge density of negative 45 nanocoulombs per meter. Since this is negatively charged, we expect the electric field to point radially towards it. So I'm going to just draw a bunch of lines representing this electric field. I would expect the electric field gets weaker as we get farther away, which we can look for the equation that describes the electric field on the test notes for this specific situation. But again, this problem is asking us to use Gauss's law. Now, as a reminder, Gauss's law is looking at the electric flux through a closed surface. We can write that as the closed integral of E dotted with area, E dot dA, meaning we have to integrate this electric field if it has different values through the area of a Gaussian surface. So we don't have a closed surface chosen yet. We get to decide that. Gauss's law also tells us that the electric flux can be calculated if we know how much charge is located within the Gaussian surface we're using, and then epsilon naught is a constant. Okay, if we're trying to find electric field using Gauss's law, we're doing so using symmetry, where we can simplify the integral down to just being E times A. Now, we can't do that just because we want to. We have to make sure we choose a closed surface. We call this a Gaussian surface. Such that E is uniform. It has the same value as it passes through the surface, and such that the electric field is parallel to the area vector. Our choice of a closed surface is when just symmetric to what we know the electric field looks like. So this line of charge, we know the electric field is going to point towards it because it is negatively charged. I want to choose a Gaussian surface. This is just an imaginary surface. It needs to be closed. So to make this closed, I'm going to choose a cylinder because this is symmetric to the line of charge. A sphere would not be symmetric. A sphere, there would be points that are closer, points that are farther away. This is not symmetric. So I would not choose a sphere. I would not choose a cube. For the same reason. Okay, so I'm choosing a cylinder in this case. And I'm choosing this cylinder such that this thin line of charge, or this thin straight wire, has its sides equally distanced from the wire. So essentially the wire, this long straight wire, is going down, traveling down the axis of the cylinder. So to use Gauss's law to solve for the electric field, we're going to look at the flux through this cylinder I've chosen. the cylinder is not a real object. It's just this imaginary closed, surface, this Gaussian surface to talk about the flux through. So I've satisfied the conditions, though. This cylinder, where the electric field passes through the edges, because the edges of the cylinder are the same distance, those side edges anyway, are the same distance from the wire, the electric field will be uniform. It will have the same value as it passes through those sides. The electric field vector is parallel to the area vector. The area vector is always normal to the surface. It does point outwards. So if I draw little area vectors on here, they point radially away from the wire. But that's still parallel to the electric field. They don't have to point they don't have to both point radially away, straight out. They just need to be parallel to each other. So straight in is fine, because those are parallel. So the flux through this cylinder can be written now as E times A, because I've satisfied these conditions with the closed surface I've chosen, this cylinder. But the flux can also be written as the charge enclosed within the cylinder divided by epsilon naught. What we're trying to do by using Gauss's law is to solve for this electric field. What is the strength? What is the value of this electric field 10 centimeters away? So ultimately, this R of my cylinder is 10 centimeters. It's a distance out to where I'm trying to find the electric field. Okay. So the electric field value we're looking for is E. This A is always the surface area the electric field lines are passing through. And it's specifically the surface area of the Gaussian surface, the closed surface. So that is the cylinder that I chose to have the symmetry. These electric field lines are only passing through the edges, the sides of the cylinder. They're not passing, no electric field through the ends. So I only need the surface area of the side. So R is 10 centimeters. L is arbitrary, really. I'm just going to call it L. This is unknown. It's however long my cylinder is, and it has to be significantly shorter than the length of the wire itself. I'm just going to leave it as L right now. Okay, so this represents the E times A. But I know flux can also be written as the charge located within the surface divided by epsilon naught. So coming back to my cylinder up here, this cylinder contains a portion of the wire. So just drawing really dark, hopefully, I need to know how much charge is on the portion of the wire that is within the cylinder I've drawn. This Qn will be related to the linear charge density they told us about in the problem. We know linear charge density, so let's go over here. We know linear charge density is total charge over total length of the wire, which we don't know either one of those, but that's okay. We don't actually need those. The charge density is also the charge within a certain segment divided by the length within that same segment. So Qn is going to be lambda times length n, but that is the length of my cylinder, this closed surface or Gaussian surface I've chosen to draw. It is unknown. That's okay. I'm going to go ahead and put lambda L over here on the right side in for Qn. So now I'm equating E times A for flux to Qn over epsilon naught for flux. Both equations represent the flux through the cylinder, and so they must equal each other. Notice L cancels here. That's why the length of this Gaussian surface I chose to draw is not important. So the electric field value, the magnitude, I assume is what we're implying here. Technically, lambda is negative. They gave us a negative value, which is why I drew my electric field lines pointing towards it. Epsilon naught, we know, is our 8.85 times 10 to the negative 12. R is the radius of the Gaussian surface. As I mentioned before, it's 10 centimeters, which I do want in meters, for my units to work out. So when I calculate this, gives negative 8093, which we need to round, of course. So the value of the electric field would essentially be approximately 8,100 newtons per coulomb. Our units, this coulomb has canceled with one of them in the denominator. This meter cancels with one of the meters. This meter cancels with the other. So the value of the electric field would be 8,100. I'm using 2 sig figs because I'm given that in the problem. I'm assuming the 10 to be significant to 2. I could write this as 8.1 kilonewtons per coulomb if we wanted. Now, the negative sign. The reason I technically get a negative answer is because lambda is negative, meaning I get a negative flux when I take charge over epsilon naught. What that means is the electric field points in towards the center of the cylinder. Okay, there's no such thing as a negative electric field. Negative is always related in these cases to a direction specifically. And so this electric field points inwards is what that means. So towards that wire that is within the cylinder I drew. They didn't ask that as part of the problem, but I wanted to mention that so you understand what that means.